Okay, let's start. So this video is about the paper called Learning Temporal Causal Representation under Non-Invertible Generation Process. This paper is about the causal representation learning, but the difference between the previous works is that it assumes non-invertible generation process. So usually there's a mixing function G in this kind of literature, like nonlinear ICA things. So this mixing function G usually maps the true latent space to the observation. And we usually assume that this G is invertible. That means that we can earn the G inverse. We can approximate this, but in this paper, we assume that the mixing function G is not invertible. This is a rare assumption in this field. However, the authors tackle that there are many non-invertible cases in the real world. We will see these cases with some examples later. And with this assumption, the non-invertible mixing function assumptions, they show the identifiability by recovering lost latent information. So what we mean by identifiability means is that we can align the recovered latent and the true latent to some extent. So I'll explain this part later, but with a short preview, most literature shows the identifiability up to the permutation and component-wise transformation, but this paper tried to show identifiability up to permutation invariant. And lastly, they introduced a model that recovers latent Z under non-invertible mixing function based on the theory they had proved. This is the quick overview of this paper, and let's move on to the problem settings. And first, we have to know what is non-invertibility in mathematical sense. Here you can see, so this one is inverse, so let's just consider the three cases. The first you can see is injective. Here it means that injective means 1-to-1 correspond, and this is surjective. This means that each point in Y should have at least one connection. So as you can see here, there's the point 4, but this is empty, but there's no empty point in this Y. And the last one is injective plus surjective, and we call this bijective. And this bijective, the condition satisfies, it is invertible. To satisfy invertibility, the function needs to be bijective. And if the function is bijective, like this, we can earn the inverse function. Right? And now, so previously we see the example of non-invertible mixing in the mathematical sense, but now let's see this example case in the real world scenario. So the authors provide two examples mainly. One is non-invertibility by occlusion, and the second one is non-invertibility by vision persistence. And one thing you have to know before this page is that this paper only assumes sequential data. Like the whole observation consists of several data points, and they are having some temporal correlation. And in this case, the occlusion, this one is not generated by invertible function because in this frame, the first frame, we can see that there's a white car here, right? But let's say this is t equal 1, and this is t equal 2, this is t equal 3, and this is t equal 4. And if you see that t equal 4, the white car is occluded. Let's say the white car is occluded by this black car. However, the true latent Z may, with high probability, it will contain the information about the white car. But by only observing this frame, we couldn't get the information about white car, right? That's because this image is dependent on the previous frames also. So the generation function would be like the x t equal 4 is generated by z t equal 4 and z t equals 3 and z t equal 2 like this. So it has 3 components in this, and it contains the historical latent value. The second example is similar to the previous one. The vision persistence means that if you capture the fast-moving object, the observation is generated from the last few frames. This is also similar case like this. And if you see the previous slide, the invertible function needs to be bijective. But this relation is not bijective, as you can see, so these are the non-invertible cases. Now let's see the specific problem set up in this paper. Let's say we have some latent variable z and the observable variable x here with its timestamp like 1, 2, and up to t. And let's say this xt is d dimension and zt is n dimension. Firstly, let's see this mixing function part. As I told you before, we assume the non-invertibility, which arises from getting historical value as an input factor. So you can write the observation at time t can be generated by ct to t minus r. Let's say we need like r steps to generate the current observable variable. Then we can write this like if we input these variables and put these into the g, we can get xt, right? Then now let's see how we can recover the latent variables from the observation. That we can use this equation. The mu is another the time lag term, the needs for recovering the latent. And let's see, we have xt minus mu here, and we need this amount of observation to get zt, and we call this mapping n. So this is the basic setting of this paper, so you have to remember this. And now I'll explain the transition part. In this part, we have to consider the time-delayed causal relation. And this transition is non-parametric and stationary. So there's stationary and non-parametric. This means that the causal graph is invariant to t, time t, right? And now let's see the equation. We have transition function f, and zit, the ith element of zt, is coming from this noise in this term. So this pa denotes parent. So the parent zit means the cause of zit. And this t prime is the time from t minus 1 to t minus tau. Any value in this range. Okay, this is the basic setup, so you have to remember this equation 1, equation 2, and equation 3. And now let's see the identifiability of latent causal representation. So if we say the learned generative models are f hat, the transition function, and p epsilon, the noise distribution, and this is also hat, and g hat, the mixing function that we can learn. And let's say the model distribution is p fi hat, p epsilon I hat, and g hat with the all data observation. And the data distribution is p true fi, p epsilon I, and g with all the observation. If we have this m that satisfy this equation, which is called observational equivariance. I'll write this observational equivariance. This is called observational equivariance, where this is the model distribution and this is the data distribution. And if this can yield this kind of relation, so this is like we assume that we can have this m and m hat, which are in relation of the permutation and component-wise transformation for all these xt to t minus mu. We called this process identifiable. And for more explanation, the first thing is about m. So this m reflect the property of g implicitly, so this m is included in this definition. And the second thing we have to remember is g is not identifiable. But we want to show that m is identifiable and showing that z, which came from m x something, we want to show the identifiability of z. So be careful that we are not showing the identifiability of the non-invertible mixing function g. And the third thing we want to say is, if this causal process is identifiable, which means that we show the identifiability of m, the causal relation, the f, is also identifiable up to the permutation and component-wise transformation. Until now, we saw the basic setting from this paper, but you may think that is the function g and m is mathematically reasonable? So the authors provide an example. So let's see this. Let's say the current observable variable is generated from the observation from t-1, which is weighted by 1/2, and the latent variable from the current timestamp. And this equation we can extend by replacing this into the another summation, and finally we can get the equation like this. So from here, what we can think is that to get x, the function g requires like infinite latent right here. So this is like infinite. However, writing this equation with respect to zt, this equation became so simple, like xt minus 1/2 xt minus 1. And by this equation, we can see that we only need t to t minus 1 observation to get the zt, right? So here we need only finite samples. And before going to the next slide, the thing I want to emphasize is this paper only considers the temporal relation, only like time delayed temporal relation. So the instantaneous relation is not considered. So we can say like zit and zjt are conditionally independent when we have history here. Okay. Now let's move on to the theorem 1, which explains about identifiability under non-invertible generated process. So we start with without loss of generality, we set the tau equal r plus 1. And let's go back to the generation function. The xt can be written as g xt to t minus r. And if r is 0, this is like the normal generation function with non-invertible process. There's no lag, right? However, if r is larger than 0, this is the case that we want to address here. This is the non-invertible generation process, but with time-delayed causal relation. And we're going to assume the second case like this, and we also set that m exists that satisfy that the ct came out of m xt to t minus mu, where mu is another time lag. In the theorem 1, we need 3 supposition. The first one is smooth and having positive density. The positive density means that we have like this relation, and also this have to be smooth function. And the second one, I told this before, the ith element of ct and the jth element of the zt is conditionally independent when we assume that the histories are given. And the third one is called sufficiency, and if you see here, there's a definition of the sufficiency, but it looks a bit complicated. So there's a definition of eta kt, which is defined as log probability of ckt conditioned on zt minus 1 to t minus r minus 1. And there's complex equation, which is defined as phi lt. And it's said that for L 1 to n, for each value of ct, there exists 2 n different values, and such that the 2 n vector functions are linearly dependent. This might sound so sudden, so I'll explain in the later part. And this theorem is that if we suppose that this 1, 2, 3 are satisfied, the permutation pi and the component-wise transformation t exist such that the zt head that we earned is the permutation and the component-wise transformation of ct with respect to the context. This context is the history values that we assume that that we can refer to. Okay, then now let's go to the proof part. Let's start from this equation with the mapping function M. This is the equation we saw before. And in the first step, we separate it into two terms. We separate xt from the upper value, and we can write the others. And then, since we know that xt is equal to g head ct to t minus r head, so xt can be written as this, and this remain the same. And from here to here, we separate the zt to t minus r head again into the two parts, which is ct head and zt minus 1 to t minus r head. And this, again, remains the same. And now we will consider this parts, which can be extended as zt minus 1 head, zt minus 2 head, and to zt minus r head, right? And each of this learned latent can be written by the mapping function m head, like this. And still, the last term remains the same. And this, the last equation implies that the mapping from zt head to zt is partially invertible function. And let's say the partially invertible mapping from zt head to zt is called h. And this h, as you can see, starts from zt head, and if it's fed to g head, it became xt. And we put xt into the mapping function m, we finally can get zt, theoretically, when it is conditioned on xt minus 1 to t minus mu minus r. And then we can rewrite this relation into equation as zt equal h, zt head conditioned on this history. And if we say this part is c, the context, and this hc means that it is conditioned on this context, and now we can write zt equal hc, zt head. If we consider the Jacobian of h, we can define the Jacobian as the partial derivation of zt to zt head, but this is actually conditioned on this history part. Based on this information, we will see another mapping called t. Now we add the conditioned history here, and let's think about having zt head here and zt here. So the Jacobian of this transformation t can be written as this, as you can see here. This is, of course, the identical matrix. And this one is Jacobian h, as we saw before. And the reason that we have 0 here is that the upper part is historical value, and this is about the current value, which has the timestamp t. So the history is not dependent on the current value, so it became 0. And for the last one, we have the current latent, and we differentiate it by the history, and this is some matrix, but we don't have to know it perfectly. So from this result, what we can see is the Jacobian is lower triangular, which allows us to calculate the determinant easily. And with respect to this joint 자르고, and with respect to the mapping T, let's write the joint PDF. We have the joint distribution zt, xt minus 1 to t minus mu minus r minus 1. And this is the probability of zt head and zt minus 1 to t minus mu minus r minus 1 divided by the determinant of Jacobian t. And by dividing each side with the probability of xt minus 1 to t minus mu minus r minus 1, we can get this conditional form. And because we can get z from the mu observation, we can rewrite this equation like equation 1. And since we know that the Jacobian of transformation t is equal to the ht, which is the determinant of the Jacobian h, and because we assume that the latent is conditionally independent to the historical values, if we write the cross derivation with respect to zit head and zjt head respectively, we can get the second derivative as 0. And given that this part, the red part, can be separated into two terms with this conditional probability, and considering that this part is irrelevant to the current latent values that we have earned. This equation denotes that the second derivative of the conditional probability is 0. So we call this equation 2, and this one is really important. Since I said the result of equation 2 is important, let's try to get this form, starting from 1. In the equation 1 is this one. Sorry, this slide is duplicated, so you don't have to care about it. And log of equation 1 can be written as this one. The multiplication became plus here. And since we define eta kt as log z kt conditioned on z t minus 1 to t minus r minus 1, you can rewrite upper equation into equation 3. We will use this equation 3 twice. First, we will get the first derivative of equation 3, and it consists of two parts, a and b. First, we will see the partial derivative with respect to the zit head. The thing you have to see here is we use the chain rule here, and this is just a derivation. And we rewrite this part as hkit, where ht is the Jacobian of jt. And we do one more derivation with respect to zjt, and the derivation of this part became this, and this part became this term. And we see the left-hand side. We have to remember that we saw this equation before. This is equation 2 here, and it is 0 that we have shown before. So this equation is 0. So let's see this as equation 4. And since 4 is 0 everywhere, the derivative of 4 with respect to the ZL t minus r minus 1 is also 0. You have to notice that we are having derivative with respect to the historical latent. Okay. So the left-hand side would be like this. And there's many terms, but most of them are having the value of 0. Usually because the ht is not dependent on the zl t minus r minus 1. And finally, we got simple form like this, and this is also equal to 0 because the derivation of 0 function is also 0. And this can be true for all L starting from 1 to n. And we call this equation as equation 5. If we say this term as LK and this term as QLK, we can write VLT as this. So what's the VLT? Let's get back to the assumption of theorem 1. You can see VLT here, and this complex equation can be written as n functions from QLK and n functions from SLK. And the assumption is that this set of 2n functions are linearly independent. And to satisfy this assumption and equation 5, the multiplication of hkit and hkjt must be 0 when I is not equal to j. What is the meaning of this? The Jacobian, the element of Jacobian, the hkit and hkjt's multiplication are 0. This means that in each row of the ht, so there's missing. Each row of ht has at most one non-zero entity. To be more specific, this means that if we have n-dimensional latent, like ct hat here, and zt, there's one-to-one correspondence. And because they have same dimensionality, this relation is bijective, thus it is having partial invertibility. And by these, we can say that zt is identifiable up to permutation and component-wise transformation. And next, we will introduce the concept of permutation invariance. While this might seem somewhat abrupt, it is important for considering more general case later on. Let's first examine the definition. So far, we have discussed identifiability up to permutation and components-wise transformation, but this time we will consider permutation invariance. So the following definition 1, the definition 1 has this equation. If the pi is fixed permutation and this t is a component-wise invertible transformation which may vary across different time steps, we call this identifiability under permutation invariance. So this time we will consider the context that this component-wise transformation property can change over time. And as I told before, let's consider the general case. Now we assume that this xt in the observational space is the dimension vector, and this z is in n dimension, the latent space. And before, you may remember that we have an assumption that assumed that Pz is smooth and positive. But now we allow this density function to have 0 value. So why do we bring this story up? In the previous section, like the theorem 1, we tried to show identifiability by showing that the Hijt multiplied by Hikt is equal to 0 when j is not equal to k, and this condition seems like it is enough for the identifiability proof, but it is actually not enough in this case. And in this case means that we can have a 0 value in the latent space. And this is because that for the linear ICA, the matrix H is constant. Remember that H is the derivative of z to z hat. And this is constant in the linear ICA. So this each elements are constant, but in the case of nonlinear ICA, this H is function of z hat, and this z hat varies in the latent space. So this may lead to failure of the identifiability. There are some examples here to show why this can be true. Let's see this example. We can rewrite this equation like this. When if x plus y is larger than 0, x is u and y is v. And if x plus y is less or equal to 0, then x is v and y is u. Okay. However, this relation is entangled. What do I mean by entangled is if we consider the mapping H starting from u and v to x to y, if one element change, it can be x or y, but let's say y, the only one element has to be changed. And similarly, if v changes, the only one element should be changed. Let's say that is x. However, let's think the case when u is 2 and v is -1. 2 plus -1 is 1, so it's this case. And here we can see that x is equal to 2 and y is equal to -1. Then let's change this value into -2. When u is -2 and v is still -1, but because u plus v is -3, which yields this case, now x is -1 and y is -2. Here, what we can see is among the input variables, only one element changes, but both the outcomes are changed, so this is entangled function. However, the Jacobian of this mapping has at most one non-zero entity. For example, if we consider the Jacobian, we can write this as delta x, delta u, delta x, delta v, and delta y, delta u, delta y, delta v, like this. For each row, this can be only 0, 1 or 1, 0. And there's no way to make this row into 0, 0. This couldn't be happened, as you can think of. So this satisfies this condition, but it is still not identifiable. Okay, and there's another case here. We also assume that we have a mapping function h, which maps u and v to x and y. And let's define f u comma v is defined like this. This is actually the clipping function with respect to the w plus v plus 0.5. We clip this in the range of 0 and 1. So if we have the axis of u plus v plus 0.5, and we have the value here, this is actually looks like this. Here's 0 and here's 1. And here's also 1. Okay? And let's say we are having -2 to -1 and 1 to 2 for all 4 values x, y, u, v. And this is also an entangled example because if we consider that u is -2 and v is -1.3, u plus v plus 0.5 is smaller than 0, so f should have the value of 0. And in this case, x is having 1v, which is equal to -1.3. And for y, because f is 0, the y is having value of u, which is -2. And all these variables are in the range here. However, we also assume that only u is changed to +2 and v is still -1.3. And here we can see that now u plus v plus 0.5 is larger than 1, so f is having a value of 1. Here, now x is having a value of u, which is 2, and y is having a value of v, which is -1.3. So only the single input, the u, is changed from -2 to +2, but both x and y are changed. So this is entangled. But similar to the uppercase, the Jacobian, each row in Jacobian can only have at most one non-zero entity, and we couldn't achieve 0, 0 here. So this is the case that we have entangled relation, but we have at most one non-zero entity. And to resolve this problem, we need 2 additional assumptions to achieve identifiability under permutation invariance. The first one is the path connected condition. This is for the latent space large Z. And this space is path connected. What do you mean by this is, if we have a space like this, and we have 4 available candidates for CT, let's say, CT head. And each point can be connected by continuous function for all the possible combination of the points. So this is called path connected. And the second assumption is that mapping function A is second order differentiable and it satisfies non-degeneracy condition. So non-degeneracy condition means that this n dimension to n dimension mapping is invertible, and this invertible function needs non-vanishing Jacobian's determinant. So these are 2 additional assumptions, and let's see several definition here. We have one more factor here. High-level setting of this paper is non-invertible generation function, but the reason of that non-invertibility came from the conditioning on what? On history. So to make it simpler, they bring the concept of partially invertibility right here. To see the whole mapping H, this is non-invertible mapping, but if you assume that it is already conditioned on history, this one is invertible. And now let's see definition. So we have the function H that got C head and C, where the C is the conditioned element, which is some observation in this case, and we got C from this. And what we mean by partially invertible is if for any given C, any given history, the rest part, this HC, is always invertible. Okay? This is not like perfectly general setting, but yeah, just let's keep going with this. And now let's see the non-degeneracy condition of partially invertible functions. The non-degeneracy condition of a partially invertible function, this one, is that for any given C, the determinant of Jacobian matrix of HC is always non-zero. So before we saw the non-degeneracy condition, that the determinant of the Jacobian of the mapping H is non-vanishing, but now we assume that that condition is applied on HC not H. Okay, this is a simple one. And now let's kind of move on to the lemma one. If two assumptions are held, which is the first one is the latent space Z hat should be path connected, and H, the mapping function, is second order differentiable, and H is non-vanishing. And this is actually HC, and here's HC too. Oh, sorry, HHC is non-vanishing. If these two assumptions are held, then the identifiability under permutation invariance is obtained by Hij multiplied by Hij is equal to 0 when J is not equal to K. So this is lemma 1, and let's prove this. First, let's consider each row in Jacobian, and that might be written like this if we consider the ith row. So this is ith row of Jacobian H, right? And if lemma 1 supposition and non-degeneracy is satisfied, the image of this ith row is in this subset. This condition came from a non-degeneracy assumption, and this is the lemma 1 supposition, and this is just the format of the row. This means that only one non-zero entity in each row, not less or not more, but only one non-zero entity. Okay, because it couldn't be all zero, but it is having at most one non-zero entity. And also because of H second order differentiable and invertible assumption, H prime is also differentiable. So what does it mean? This denotes that since this latent space, the Z hat, is path connected as our assumption, the first order derivation is also path connected. We can think that this latent spaces correspond to the mapping H, because this H is on the same level as the latent, and we can consider that H hat corresponds to this derivation. So we can say that this first order derivative result is also path connected. We have to remember this. And now they use contradiction to prove this lemma. So this is current situation of the Jacobian. If we consider the ith row, let's assume that we have two non-zero options in the latent space Z hat. If we say the jth element in the ith row is 0, like this, when the Z hat is equal to A and A is in the set large Z hat, and this can be written as the row ith row when Z hat is A and we are seeing the jth element is non-zero, we can write the full form like this. And now let's see when Z hat is equal to B and this B is also in the latent space. And let's consider when the kth column in the ith row is not 0 when the Z hat is B, we can write this in this notation. We have non-zero value here. And like for simplicity, we can write for this vector, and for this vector, there's no paths from here to here, right? So this is a contradiction. To satisfy the assumption and supposition, these, like Z hat equal A and Z hat equal B, should be path connected, but they are not. So this is contradiction. So the lemma 1 is proved. And lemma 2 is really similar to lemma 1. It is just like under side information. We have the same assumption here, the second order differentiable invertible function H, defined on a path connected domain C hat, but multiplied by the sign information C dimension. And we have the mapping function like this. And we also suppose the non-degeneracy condition. We say that if there exists at most one non-zero entity in each row of the Jacobian matrix, the identifiability under permutation invariance can be established. The proof is really similar to lemma 1, so I'll not go deeply into this. And now let's finally move on to the model part. So here you can see the overall figure of the querying. You can see encoder here, decoder here, latent and recovered observation, and we can also see some inverse transition function here. We will see these one by one. The first one is encoder decoder module. As you can see, the shape tells us that this is like autoencoder And we call this sequence-to-step encoder, and we call the decoder as step-to-step decoder. The reason is that this encoder got some sequence of observation like this, not only getting a single steps observation, but rather than that, we are getting a sequence. And then we map this into the latent of the specific time step. Let's say the t is equal to 2. And we can write this encoder as q pi, where the pi is the parameter of the encoder. And this is conditioned on the history. And we are modeling the distribution of the latent variable. And for the decoder, this is step-to-step decoder because we got the single step input and we got single step output. So we call this decoder p theta xt condition on zt. This is kind of normal. And this architecture is based on the sequential VAE. To see a bit more, this architecture is based on sequential VAE from Chen et al. In Europe's 2015. And let's see background. The first one is sequential modeling, and we will also see VAE part. But for the sequential modeling part first, we have this nonlinear transition here. And to earn this hidden state, we need observation of the current state and the hidden state from the previous step. And when using the joint sequence probability distribution like this, probability of the data from x1 to xt, we can write these as the factorial form of the conditioning probability, where pxt conditioned on x history is equal to g tau ht minus 1. Let's say we have this relation. And we will also see the background of VAE. As you may all know, we have random latent variable z in VAE part, and we can write the joint distribution of x and z as pz multiplied by px conditioned on z. And we assume that this pz is a simple distribution. Let's say this is Gaussian, and we also want to model the px conditioned on z by an arbitrary observation model. And this arbitrary observation model is usually neural network, which is highly nonlinear. Because we assume that this px condition on z is really complex function, the qz condition on x is intractable. Because it is intractable, we try to use approximation using lower bound. We use the relation that the log probability of x is always larger than the minus scale divergence between q probability and prior plus expectation of the log p condition on z, as you can see here. And by using this lower bound equation, we jointly training p x conditioned on z and q z conditioned on x, which is decoder and encoder. And now let's see what sequential VAE is. This is similar to normal VAE, but we are conditioning on ht-1. So the prior on z is no longer standard Gaussian, but instead of that, we have the normal distribution of mu 0t and diagonal of sigma 0t square, but the conditional prior distribution, the set of mu and sigma, came out from this phi tau prior ht-1. And as I mentioned here, the phi functions are the functions that extract parameters. And also generating distribution also relies on ht-1. The xt condition on zt follows the normal the Gaussian distribution, but also this mean and the standard deviation value came from the extraction function, where the input is phi tau z ct and ht-1. So it is also conditioned on ht-1. So the modified elbow looks like this. You can see that we are also having the history of latent in Q, also in here. And for this part, we have the history observation here too. So this is sequential VA. And let's move on to the prior estimation module. This paper mentioned that they used the normalizing flow. But to say in simpler way, this is just like prior estimation module instead of just using the simple distribution like Gaussian distribution. We have seen this equation before, right? This is the stationary and non-parametric transition, which maps the historical latent and the noise to the current ith element of the latent value. And we try to get the inverse function of this transition function. And this is defined like this. So we're trying to learn the prior. This is actually the result we got, but we will see how we can derive this equation. So first we consider a mapping A, which maps from the z hat history and z hat current latent value to z hat history and epsilon t hat. If we write the Jacobian matrix of this mapping A, we can write like this, and this is of course the identical matrix. This one is obviously 0 because in the upper part we have history and in the lower part we have the current latent value. And this one is also 0 because noise is independent to the historical latent value. And this one, the index of epsilon t and zt has to be same, not to be cancelled out. So we only have the diagonal values. By this, we can see that the Jacobian of the mapping A is lower triangular. So it is easy to calculate the determinant. And the joint PDF can be written as like this equation. As I told before, we are going to get this quantity. First of all, we divide this conditional form into the two terms because the P, the conditioning, blah, blah, is equal to the joint probability history over probability of the history head. And because we use a log here, the division became minus here. And this part remains the same. But we show that this can be written with the joint PDF as we have shown here. So we use this equation here. And we combine the first term and the last term to make log probability of the noise t hat conditioned on the history latent variables, and we still have this plus log determinant of j. And because this epsilon t hat and the history latent values are independent, we can just simplify the term like log probability of epsilon t hat. To enforcing the conditional independence, we can write this probability like the summation of each component, and we finally can rewrite the equation like this, and this part is easy to calculate because the Jacobian is lower triangular. Finally, if you see the optimization, the loss function consists of two parts, the reconstruction part, which came from the encoder-decoder module, and the scale divergency part. And especially this, for the prior, we use the normalizing flow to get the inverse dynamic of transition function. So finally, we can optimize the model. And finally, let's see the experiments. They mainly use two datasets. The first one is video QA. The second is SUTD traffic QA. It is kind of interesting to think that they use this causal representation learning module into the real-world dataset. And they have two tests. The first one is NG, and the second one is NGTD-MP. This sounds unfamiliar, but this is just like non-invertible generation, which we have R is 0. So the encoder is not like sequence to step encoder, but just step to step encoder as usual. But this NGTD-MP is like non-invertible generating function with temporal delayed mixing process. So this is the case with R is larger to 0, and this considered the time delayed causal relation. The evaluation metric is MCC. And we're not going to see the experiment parts deeply, but we can see that this is one of our baseline model called TDRL. And this is the correlation map of the latent Z1, Z2, Z3. And we can see that the carrying has strong correlation here, while the TDRL failed to get the correlation in some latent variables. And these are more baseline models, and we can see that for the MCC comparison, with larger and larger epoch, the carrying shows MCC score almost to 1. And this is an example of experiment. They use HCR and encoder and step-to-step decoder and prior network, which is which is a slightly modified architecture of the basic hearing to apply this into the real-world dataset. And this HCRN is hierarchical conditional relation network for multimodal video question answering. And the dataset is like, could the accident be prevented if all of the vehicles drive in the correct direction? And this hearing tries to find a true latent space so that it can get a better performance in the QA task. So this is all from today. Thank you for listening.